Okay. Now it is okay.
Yeah,
It
that's
is.
okay. Yeah.
Yeah.
I have been some problems with the share screen on this computer, so let's see if everything goes right. So good morning to you all. Thank you for the opportunity to present my work on this session. I want to thank the conveners for their welcome. Um, so I'm going to talk about cosmic strings in generalized hybrid metric-Platini gravity. It's under the scope of my master's degree. I have been doing my master's degree with Francisco Lobo from Lisbon and Pedro Avelino from Porto, and this work was done with the invaluable help of Tiberio Arco and João Rosa that will present later in this meeting. So I'm going to talk to you a bit about the hybrid metric-Platini. Then I'm going to make a quick reference to cosmic strings because you all are very familiar with cosmic strings. And then we're going to look at some of the things we got from our analysis. So the motivation for modified gravity, so hybrid metric-Platini is the modification of the Einstein field equations. It's that we have an imbalance caused by the recent cosmic late time acceleration, and the way physics deals with this kind of imbalances usually goes one of two ways. Either we have previously unaccounted source, for instance, the cosmological constant, which has problems by itself, um, or we change the governing equations, and there's where the modified gravity enters. We are limited in some way by Lovelock's theorem on what we can do to modify gravity, but I like to look at Lovelock's theorem in a different way. I like to look at it as a roadmap to what we can do by changing the gravity equations. So it really tells us what we have to do to modify the equations. So we've been working. A lot of people have been working on modified gravity, and the idea is look for more general curvature invariants that may account for late time acceleration without the need to invoke dark energy, um, and also to explain large scale dynamics of self-gravitating systems without invoking dark matter. So the hybrid metric-Platini is that we know that the metric and the Platini approach, they are successful in reproducing the accelerator rate that we see in the universe, but they are fundamentally flawed when it comes to change the solar system dynamics. We know that GR is very well studied. Actually, it's the only place where it's very well studied is in the range of our solar system. So changing the solar system dynamics is a deal breaker when it comes to modified gravities. So a new approach was proposed, the hybrid metric-Platini, in which we construct the action not only with the Ricci scalar, but also with, let's call it the Platini scalar, in which we construct the Platini scalar based on this independent connection. So this connection is not the Lev-Civita connection of the metric; it's the Lev-Civita connection of a metric that is conformally related to the metric. So this has one enormous advantage, this hybrid metric-Platini, besides generating long-range forces that can overcome the solar system tests. It allows for a scalar-tensor representation, which simplifies greater the equations, in which, in this case, we have two scalar fields, as you can see here, and then one can write the dynamic equations This is the dynamic equations for the field, and this is our the Klein-Gordon equations for the scalar, both scalar fields. So it is with this that we are going to apply to the strings configurations to see if we get solutions. The motivation to study the string solutions in this hybrid metric-Platini comes from the fact that as you can probably see here, this is resembles very much with Brunsticky if we replace this by the Brunsticky factor by -3/2. The difference is obviously this coupling factor here. In Brunsticky, if we try to study strings in Brunsticky theory, we don't get solutions unless we introduce a cosmological constant in the action. So here we try to find if we, in the hybrid metric-Platini case, we do find solutions without the invoking the cosmological constant. So cosmic strings, they are topological defects that are formed during phase transitions after spontaneous symmetry breaking. They are featured in several grand unified scenarios. They are closely linked to the initial expansion of the universe, so the inflation phase. If they are formed too early, they become diluted by the inflation. If they form too late, these topological defects will probably dominate dynamically the universe. So they are very dependent on the moment of formation, and the symmetry breaking scale will also impact on the energy of these topological defects. We can have strings, we can have domain walls, we can have or other sort of defects that will essentially depend on the topology of the minima manifold. This we studied strings because they are more favorable by the recent observations. Walls have the difficulty of becoming dominant in many scenarios. So we to study this we use a straight infinite cosmic string. I know this is not the most general case because here we are ignoring the pressure on the direction perpendicular to the string. So we should have more terms here. So this is not a general case, it's just a simple case to study its properties. So sigma is the string tension, and then we consider a cylindrical symmetric static metric of this kind, where we have K, U, and W here that are dependent on the radius of the configuration. If we demand that the conservation equation holds, and also if we have boost invariance along the string, along the T and Z directions, so the directions of the string, this simplifies, and the only surviving element of the metric will be this W factor here. So if we get now the full dynamical equations, here we have the W, so the only surviving component of the metric. We have here U and V that are, as you can see here, the derivatives of both scalar fields, and then we have here a function of the energy density of the string. As you can see, this is dependent on V, so on the potential that we put on the action, and we are going to see what happens. So we need to specify a potential function that will depend on both both scalar fields, And we also need a set of boundary values. So we need the boundary values of the scalar fields, of the derivative of the scalar fields, and also of the metric component to at the radius of the string. Also, more parameters can appear on the form of the potential. So given the potential, we may have more parameters in this parameter space. So as you can see, the parameter space will be enormous. So we'll have a multitude of solutions. One of the things I'd like to point out is that this W0 component, so the value of the of the of the W function in the metric, it's not zero at the radius of the string. So we can't exactly call it an axis. That's almost a philosophical discussion, whether we call it an axis or not. So exact solutions that we found given the potential. So we found two exact solutions. One of them is the trivial solution in which the potential is zero. I want to call up your attention for the form of the energy density of the string. As you can see, the energy density of the string will be negative for all radius of the string. I won't dwell a lot on this, but what I've learned is that this has some applications on traversable wormholes, but I don't know enough about this to talk to you about this. But this is an interesting. There can be applications on wormhole studies. Another solution that we found, another exact solution, is when we set the potential function to be a constant. In this case, we call it a lambda function. In this case, you can see here that for large radius, the string tension does not tend to zero, but instead it tends to the value of the cosmological constant. So that means that at large distance from the radius of the string tension will match the cosmological constant. So these were the exact solutions that we found. And now about numerical solutions, I won't show you all the solutions. If you want, you have the link for the paper in the presentation. You can see that we studied all these types of solutions. Remember that I told you that we have to set the parameters of the values for the fields, for instance, at the center of the string. Here comes the other parameters that we can modify, A, B, for instance, this small lambdas here, etc. So what we learned from this is this, like in Bronsdicke gravity, we found string solutions in generalized hybrid metric-Platini without invoking the dark end, so the lambda. String tension is not necessarily positive. We showed you that if the potential is zero, we get a string that has negative energy density. The numbers of the parameters of the models allow a wide range of solutions. This must be then matched to exterior solutions to the string. And the solutions are very, very sensitive on the initial conditions. If we change just a bit the initial conditions, we get very, very different solutions that are not asymptotically flat. As an example, I'll show you the behavior of the string tension in two situations. So this on the left side is this potential of this form here, and that we change the value of A. And this one is the string tension for this potential here, also changing the value of A. As you can see, this one doesn't tend to zero, so it has to be matched with a background value. And this one is some kind of damped harmonic oscillation, and it also has to be matched with an exterior solution. So we need to define the radius of the string. Usually the radius will be defined as the value when the tension goes to 0. In this case, for instance, it doesn't go to 0 for any value. So what we need is to match this value with the background value. Maybe can be the mean density of the universe, for instance. And
Sorry for bothering you. Yeah, 3 more minutes. Yeah.
no,
So,
I'm finished.
oh,
I'm finished. Okay,
that's great. Amazing.
thank you. So I'm going to stop share.
So we take 1 or 2 quick questions.
Yeah, I have a question,
Yes,
Roberto.
yes. Go, go.
Did you also consider the Mexican head potential, the quartic potential in the scalar field?
No, we did not. The classical maximum potential, we did not.
Okay.
I'll have to
But-
check on the.
But when your scalar field phi is equals psi, you have a scalar field to the power 4. Isn't that correct?
Let me just confirm the. Give me just 1 second to confirm here. So you are saying the.
Yeah, you can recover the famous phi to the power 4 model when your scalar fields are equal, your two scalar fields, or not?
I know we studied the power for potential in earlier work that we did, in which we didn't consider 2 scalar fields, we considered just 1 scalar field. So this is the generalization of I remember that we studied the potential the potential of this type.
Okay. Thank you.
Thank you.
Thank you so much for the talk. Thank
Thank
you.
you. Thank you.
So let's welcome our next speaker, Reinhold. So he's going to talk about some new evidence of azimuth alignment of Pulsar spins. So it's fine if you just share your screen and.
Yeah, I can share screen. Okay. Did you see my screen now?
Yeah, we can
Okay.
see your screen. Yeah, but little bit. There is
Too
bit
large?
not. Yeah. There is a missing of alignment here.
Is so okay? Can everybody
Yeah.
read this?
Yeah. Now it's okay. You can start it.
I can make it a little bit smaller, so, or
It is
larger.
okay. Yeah, it is okay.
So?
Yeah, sure. Now,
Okay.
right. So you can start it. Thank you.
Okay. Thank you, Batul, for the introduction. Well, I will talk about the evidence of cosmic strings by the azimuthal angle alignment in large quasar groups. And I will give an overview. I will explain very shortly the basics of the vortex solution in connection with superconductivity, the Nielsen-Alderson phi to the power 4 model, and then the self-gravitating U1 cosmic string solution. And I will consider the space-time on a 5-dimensional space-time in the Randall Central model. I will explain why I do that calculations. I will use the multiple scale approximation and then the breaking of the axial symmetry. And then the data from NASA IPEC to prove that the quasar spin vectors alignment could be an indication of the existence of cosmic strings. Well, here you see some publications. Well, superconductivity, we all know that the abelian U1 scalar field has lived up its reputation as the famous Ginzburg-Landau model to explain superconductivity. The order parameter phi is, you can say, equal the Higgs potential in the standard model. So we have 2 famous applications in the standard model and the superconductivity. So we have the relativistic Nielsen-Alderson vortex solution, the self-gravitating solutions, and there's a connection with supermassive cosmic string solutions. they can build up huge mass in the extra dimension. And that can be very interesting by the application to quasars. And now we apply the breaking of the axial symmetry of the azimuthal angle. You can say it's a kind of second order phasor transition, and can it cause the alignment of the quasar spin vectors? And so will it be of primordial origin, the alignment? Well, very shortly, even the superconductivity. We all know the famous Meissner effect, when you have a metal cylinder and at high temperature and the temperature drops, then it turns out that the magnetic field is expelled from the cylinder and we get a superconducting ring. And the flux is trapped, is quantized. You can easily do the calculation. You see here that the flux is proportional to an integer n. Well, this is the behavior of the scalar field and the magnetic field. You can read it back in any textbook on this. Then because of vortices, when we increase the external magnetic fields, then there appear to be three regions: the normal state, the mixed state, and the Meissner effect. At a critical value of the magnetic field, the superconducting state breaks down and vortices are formed where the normal state is re-established. And that is observed by Ablikosov some years ago, experimental observed. And you see here a pattern of the regions, the vortices. They are arranged in a hexagonal system. And here I plotted in a picture. You see here the flux, the vortices arranged in this form. Then the relativistic formulation of the scalar field. Here you see the famous Lagrangian. Note that this is also the Lagrangian of the standard model of physics. The Maxwell field, the scalar field, and this is the Maxwell net potential. This is at high temperature. We have one vacuum value, and when the temperature drops, you see here the symmetry break, and the real vacuum is here in a ring around the v-axis. This is now a false vacuum situation. Here you see the parameterization of the scalar field, and it's the winding number or topological charge. This is the gauge field, the Maxwell potential, and this is the gauge covariant drive. We say that when the Higgs field makes a closed curve around a string-like configuration, then the phasor jumps by a factor 2 pi times n. And again, the magnetic flux is quantized. Well, the Nielsen-Ollerson vortex, the number string, we have two characteristic lengths, the coherence length and the penetration length, scalar field and magnetic field. And there is a case invariance, but the vacuum is not. That means that the electromagnetic gauge symmetry is broken. And we say that there's a spatial localized structure around. V has a non-trivial winding. It is a topological defect. Well, he better also mentioned this structure. So it is well known from the theory of cosmic strings. We say that the zeros of phi are a finite set of isolated points with multiplicity, this Na and so on. And the number, the winding number of phi along the circle at finite is then the sum of all the partial winding numbers. Well, the proof is very nice mathematically. We use single valueness. I will not explain it. You can read it back at my homepage if you like. But it is clear that we map the degenerated minima of the potential to the position space. You see, this is the false vacuum and is mapped on the real space, and it forms a string of points in real space. Then note that a string with one flux quanta is topological stable, as the ground state. A configuration with n flux quanta is unstable. Well, I will use this to explain the alignment of the quasars, because the energy of some configuration is proportional to n squared. So the distribution of n quanta, n is one quanta, will be energetically favorable. We call it the ground state. Here you see the formation of the cosmic string. This is the Higgs field at high temperature. And then when the temperature drops, you see there's one point which cannot follow the symmetry of the space-time, and this is trapped. The energy is trapped in one point, and the collection of all these points forms a cosmic string. Then the excitation of vortices during from quantum fluctuation during the phase of the vortex can excite to n much larger than n-1, and then it decays into n unit flux vortices, the well-known abricots of hexagonal letters. You see here a picture of the vortices. Well, this is in Euclidean space. Now I will consider this in the non-flat space-time, and then we will see that there is a remnant of the azimuthal angle. And picture here what is happening at a non-flat space-time. What about the stability? Well, it is a very complicated issue. How do they interact when gravity comes into play? But and there's another effect. We call it the semi-Meissner effect. That's when the cooling down appears, that there are groups of vortices located from a certain distance, and that could be also interesting in my model. Well, the general relativistic strings we have now, gravity. This is the space-time. You see here the usual space-time in polar coordinates. This is the extra dimension. This is in wow factor. It turns out very shortly that from the 5-dimensional Einstein equations, we get this one, and you can solve it exactly. That was published in this journal, and you see here the expression. This is the well-known Randall syndrome wow factor, and this is the time-dependent, rho t-dependent term. You can make a plot, and why do we consider the 5-dimensional? Now we shall see that the wow factor enters in the effective 4-dimensional equations, and that is very interesting. That makes produce the possibility that the effects of the cosmic string become large, supermassive, and otherwise it's known that the cosmic strings has no significant contribution to the density fluctuations, so it could be changed when you consider the 5-dimensional Randall syndrome spacetime. Here you see the effective 4-dimensional equations, and this is the meta term. This is a second order, and this is the epsilon is the contribution from the 5-dimensional wild tensor on the brain. That is the only term which will be important. No, these are the scalar field and the natural equations. We have some problems in the cosmic strings here. Till date, there's no observational evidence, no angle deficit observed. The mass per unit length is this order, so the contribution is negligible from the observations from WAMP and COPE and the CMP. So they cannot provide satisfactory explanation of the initial puzzle. So you could say this is the exit of cosmic strings. Note that only cosmic strings are survivors of the inflation. Domain walls and monopoles, they probably will not survive inflation. Well, the rescue is, could we make supermassive cosmic strings so that the effective scale is much larger than 1 and not the 10 to the power -7 as here predicted. So the phase of transition at energy much higher than the gut scale. Suppose they will be warped down to gut scale on the brain by the 5-dimensional wow factor. So then we have no singularities, as we shall see, no conflict with observational bounds. And there is a contribution from the gravitation field outside the brain. There's the so-called Kaluza-Klein modes, and they are massive from the brain viewpoint. So cosmic can also be used in superstring theory. That is demand in this model, and it could be detectable at certain Kaluza-Klein modes. And is there a quasar connection? Well, I will now go to the quasar application. The Kibble mechanism, we know that there is a kind of scale invariance when these strings are formed, and you see here in picture I draw there's a spin-off of this Kibble mechanism that suppose we have here the formation of the azimuthal angle dependency in the formation of the collection of vortices, the Abrikosov domains, and it could be translated to the alignment of quasars in a large quasar group. That is in fact the idea, that it is of primordial origin just after the symmetry breaking. Well, we have results from several years ago about the alignment of quasars spin factors, and the work was done by Hutzenmaker about 2012 and Taylor in the radio window, and they found the same result, that in the optical range there's an orientation of the polarization factor. Well, that is interesting, but to my opinion, not enough. You use the light emitted from the polarized light emitted from the quasars, and you see here the direction, and there is statistically you can prove that is very unlikely, exceedingly unlikely that it is randomly. So here you plot the polarization angle, and there is indeed a correlation. But we can do better. We can use a three-dimensional orientation of the polarization of the spin factor, not the polarization observation, but we just calculate the azimuthal and the polar angles of the host galaxy. And then we find some interesting correlation. We use the nonlinear approximation method. Well, very shortly proposed here is that we consider a formal series, and we expand our field variables in this way. There's omega, an expansion parameter, and we consider the several functions as function of the space-time and an extra variable, the fast scale. Well, it is a very null approximation, you can read it back, and it is a nonlinear approximation and suitable for situations where the curvature in the beginning of the universe is very high. And when we substitute this expansion into the field equations, you see here, for example, the metric expansion, here you see the gauge field expansion, the scalar field expansion to second order, then you get, when you collect terms of the several omega orders to highest order, you get equations, the Einstein equations, and you see here entering the contribution from the bulk. It is zero when you consider conventional four dimensional, but here you see the contribution from the bulk. This is the scalar highest order, and this is there are well-known equations. Here you see, in fact, when L mu is zero, you have the well-known condition, gauge condition, but it follows now directly from the approximation. Can normally one say this is zero, otherwise the dot psi is zero, and this is okay. When you suppose this is zero, then you have the ICRANet approximation, but it follows directly from my approximation scheme. Okay, here you see this this possibility. Then the next order, this is the Einstein equation. You see here the correction term. This is the usual background, and here you see the contributions of the several terms. You can integrate about the fast scale, and then you see here nicely the back reaction of the several terms on your normal, your standard Einstein equations. This is the normal contributions. This is from the bulk, and here you see the contribution. Then we parameterize now the several orders in different winding numbers. That is essential here. We have here three winding numbers because we have three independent. These are the perturbations, this is the background, and what happens if you substitute this in the equations? Well, we break up the perturbative way, the original vortex in winding numbers Ni. The stability issue depends on the warp factor, and we see an interaction of the gauge field with the gravitational component. This is also note. Oh yeah, when we normally when apply the Boccamolni bound, it means that the mass of the gauge field are equals, then you have a nice system. But in the multiple scale, it is a genuine feature. We don't need this assumption. It makes it more general. Well, then some results. Here you see the scalar field. If this is 0, you have here the standard Klein-Gordon equation. This is the contribution from the perturbations. See, integral over the fast scale. This is the next order, the first order time derivative of the disturbance, and then we observe. That's very easy to calculate. You can do it in Maple or Mathematics. You see here the appearance of a sine function of the two integers. So when they are not equal, then you see the breaking of the azimuthal angle. The axial symmetry is broken. Well, it turns out that the first order can write in this equation, that's not so important. And we see in the equation for the background A already terms like sine and cosine. So the axial symmetry is broken to first order. This is the next order. You get equations for the next order. You can all write down all these equations. They're a very, very huge set of equations. And the second order, they are more complex. You cannot solve that exactly, of course, only numerical. Here you see some terms I wrote down. This is the non-diagonal contribution of expressions from the energy momentum tensor. And normally this is 0, but there is no off-diagonal element. And you see here the next order there appears the sine function. This is the, yeah.
2 more minutes.
5 minutes? 5 minutes?
2 more minutes.
Okay, here you see the next order and complicated, but you see also terms like cosinus n2. And here you see ook n3 minus n1. So what is now this is the TT component. What is now the idea of the symmetry breaking? We say that when temperature drops, the azimuthal angle appears in the equations. You see, because these terms. And when you study these contributions, there will be also a wow factor. Present here you see, for example, the appearance of the wow factor. So when your wow factor is very small in the beginning, this is a huge contribution. And this is and when the evolution starts and this is large, then this is large compared to this. But this starts this approaching to 0. So the excitation of the vortex will break the translational symmetry, also in the z direction. And well, this is the connection with the Maclaurin-Jacobi. Before you can read it back on us, it's not so important. Then the data. Well, I plotted here some data from the NASA IPAC database, and you see here when you have two large quasar groups, you see here evidently the alignment of the spin factors. You see a nice, and this is statistically not randomly explained. This is a genuine feature of the quasar group. This is also a nice one where here I plotted the sign, the three goniometric functions, and you see here a nice map from the second order and the first order. And the top, yeah, will be determined by the wow factor. So this is an agreement with the theory. So you could explain, in fact, the different peaks in your alignment, because we have these terms, the cosinus and the cosine, and 3 minus and 1. Here you see some other data. It was 2 years ago, and you see here again, evidently the different peaks in the distribution. This is how you calculate very easily the azimuthal and the polar angle. So this is my summary. Observation evidence could be from the large quasar group. Okay, thank you.
Thank you so much. And also one quick question. Okay, let me have one question actually.
Yes.
So, is there any dependency of azimuthal angle on the winding number?
Yeah.
I mean, is
Yeah.
there any?
It depends on the winding number. Yes. There's
Okay.
the idea is that the vortex will be
Hmm.
excited by fluctuations to a higher winding number. It
Okay.
it will be go down to a distribution of n separated vortex with one unit of flux quanta, and
Okay.
that means that there is there will be left over a phi dependency, because when, for example, the sine n2 minus n1 becomes 0, then the cosine is just on its maximum. So
Okay.
there will be a leftover from the okay, these terms can be done, but also the sine and cos contribution in the equations.
Yeah. Okay. Okay. Got
So
it.
here you
Thank.
see, for example, in
Yeah.
this, the sine contribution here in cosine,
Hmm.
here sine and the cosine. This is
Oh,
the essence. Okay?
yeah. 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 I got it. Got it. Thank you so much.
Okay,
So,
I will
yeah.
close my screen. Okay?
Thank you so much.
Okay.
So let's welcome our next speaker, Simon Blassie. So, who's going to talk about the cosmic strings and pulsar timings? So, might be about something about nanographs, if I'm not
Yes,
wrong.
yes.
So, let's, yeah, thank you.
Hi.
Can
Um,
I see your screen?
yes, shall I share my screen? Sorry, can you hear me?
Yeah, yeah,
Yes.
I can hear you.
Ah, okay, that's good. Uh,
Yeah, we can see your screen now.
okay, that's good.
Yeah, just go ahead. Thank you.
Thank you. All right. Okay, then yeah. Thank you for having me here today. As we said, I'm gonna discuss about cosmic strings and pulsar timing. And of course, this title refers to the recent, okay, not so much recent anymore, but the recent, the last release by the Nanograph collaboration that is somehow hinting to a detection of a spectrum of gravitational waves. So let me first discuss a bit the idea of this measurement. So this relies on a method which is pulsar timing, and of course it makes use of pulsars, which as we know are neutron stars of a radius of order 10 kilometers, which have large magnetic fields and have a strong emission along the poles of the magnetic field, such that when these beams cross the line of sight between the Earth and the pulsar, we see very precise ticks. And so the way pulsars are used is to basically measure time. They are indeed great clocks due to the rapid rotation and the large inertia they have. And so here I'm showing a small table with the population of pulsars, and indeed the ones that are exploited to perform these measurements within, for instance, the nanograph collaborations are millisecond pulsars, which are the ones in the left bottom corner, which, as you can see, have a super small period derivative, which means that their frequency, their orbits are their rotation is very stable, and that's why we can use them as, let's say, almost perfect clocks. So the principle of the measurements that are employed to perform, for instance, gravitational wave searches is very simple. You need to observe the pulsar and to measure the time of arrival of these ticks when the beam crosses the line of sight with the Earth. And in principle, what you have to do then is to somehow related to the solar system barycenter, because you sort of need to be in an inertial frame. And of course, this measuring the exact time of arrival is very, very challenging from the, because there are many effects that can affect the propagation of the light. For instance, the scattering with the interstellar medium. So of course, this measurement is very challenging. And but let's assume that we kind of have the time of arrivals. What you need to do is then to find a theoretical model that fits the time of arrivals in terms of the quantities that you already know about the pulsar, for instance, the frequency and the frequency derivative. And so these models, of course, are very complicated because they need to include several effects. For instance, the fact that the pulsar is, these millisecond pulsars are all in a binary system. So there are effects of the companion star that also can enter. But then once these effects are taken into account, you are able to predict when the next tick, let's say, or the next beam will be seen from the Earth. And then basically you construct what is called the time residuals, which is simply the difference between the expected time of arrival and the time of arrival that you measure. So once these residuals are available, you can then try to search in your data if there is some unaccounted for physics in the residuals. And of course, let's say a very interesting case would be, of course, to have a modification of, a non-zero residual due to the fact that, for instance, a gravitational wave is passing between the Earth and the pulsar. Of course, the passing of the gravitational wave somehow stretches the space, and therefore between the Earth and the pulsar, and somehow introduces, as you can imagine, a time residual that you would not account with the model for the pulsar. And if you now put some numbers for a possible case, for instance, a supermassive black hole binary, which is at the distance of 100 megaparsec, you see that this will imply a residual of the order of nanoseconds for the frequencies that are relevant for pulsar timing. And but this number, which is very small anyway, is of the order of the current capability of timing pulsars, which then makes this kind of measurement possible in the first place. But of course, let's assume that now you see some sort of red noise in the residuals for a given pulsar. How can you be sure that this is a gravitational wave? Because such a signal or such an effect in the residuals can be due to other sources which have nothing to do with the gravitational waves. In particular, this could be due to an offset of the clock, or for instance, due to a misplaced solar system barycenter, because as I said, you always need to translate the time of arrivals to this inertial frame. And, or more generally, this could also be to some physics of the source, which is not really under control. And then what is the way that this is somehow, what can we do against this? How can we fight this? The idea is that you look at correlation of time of arrivals for pairs of pulsars. And so if you start looking at correlation, you can somehow discriminate these different sources of noise. In particular, if you just have an offset for the clock of the pulsars, you would see some monopolar correlation. Whereas if the issue is due to, this effect is due to the solar system barycenter, you would see some dipolar. But what really characterizes gravitational waves is the presence of a quadrupolar correlation, which is due to the quadrupolar nature of the gravitational wave. And this correlation depends only on the angle between two pulsars. And this is basically shown here via this what is called the Ellings and Downs curve, which gives you the expected correlation in case this is really a gravitational wave. So this kind of measurements require a large array of pulsars that need to be timed. And once this array is built, somehow you can take pairs of these pulsars and construct these cross correlations. And this will give you information on the kind of data or signal that you're seeing. Let me also show a bit for comparison how pulsar timing compares to the other known gravitational wave experiments, current and also future. And you see that pulsar timing is really something that works at the nanohertz frequency. This is because, I mean, the lower, let's say, cutoff is due to the fact that you can observe the pulsars only for a finite amount of time, which is of the order of 10 years. And the upper cutoff is due to the fact that you cannot take data continuously. So this is really something that works at this very, very low frequencies. But then you can go pretty low with the strain due to the gravitational wave. And now there is, in fact, this pulsar timing experiments are now converging in what is called a PTA, so the International Pulsar Timing, that somehow connects all the different experiments. So let me now discuss briefly what is in the nanograph 12.5-year dataset. So first of all, the collaboration is, of course, always increasing the number of pulsars that they are including in the dataset, and now we are they are considering more than 40 millisecond pulsars for this measurement. And what is seen in the data is a clear detection of a common red process, so which is now fitted by, well, okay, which is customarily fitted by a power law signal. So basically, such a process would be something that is common indeed to all the 43 pulsars that are considered. And you can see here that this is now detected with rather clear significance somehow. And if you compare, for instance, the Bayes factor for, if you compare this common process that is affecting all the pulsars at the same time with intrinsic noise, you get a Bayes factor of order 1000 or so. So this is a clear detection. And now you can also show contours, let's say, of what is the, what is the actual power law that best fits the data. And then you get this sort of contours in the, let's say, gamma and amplitude plane. So this dotted line is what you would get from black holes, primordial black holes. Sorry, just black holes. And so, which is one astrophysical source that is expected to contribute to, which is expected to show up at some point. And but of course, what is very important to check is what is the correlation. And the result from the analysis that is available is that monopolar and dipolar correlation, so the offset of the clock or the solar system barycenter misplacement, are actually disfavored with respect to no correlation, which is very important because it tells you that if there is something going on, is not one of the typical, let's say, issues. But what is still lacking is the evidence for a quadrupolar correlation for the data. And so if you see this plot, which kind of shows the Ellingson and Downs curve, you see that, okay, you may say that, yeah, the data can fit it, but of course this is also compatible with no angular correlation at all, which makes indeed the evidence for gravitational wave inconclusive. But this is somehow also expected in a sense that you will first see the common red process, and then only after including more data, you will then be able to see the actual correlation. So this is somehow, let's say, still expected in the for this kind of measurement. So of course, after these results were available, there has been a lot of activity in trying to explain this signal in terms of gravitational waves. And now I'm just dividing the two, let's say, possible sources of the gravitational wave. So on one hand, we have the astrophysical sources, which would be, in this case, supermassive black hole binaries, but not like single binaries, but rather a stochastic background coming from the superposition of all the, let's say, all these supermassive black hole binaries that somehow at these frequencies that nanograv is sensitive to, they produce this theoretical minus 2/3 exponent that is fitted from the nanograph collaboration. Because as you see here, this is a plot. It's basically a somehow a mock population of these binaries, and then you see that at the frequencies for nanograph, they indeed add up to this power law. But then, of course, if there were single sources which are, for instance, nearby, you would see some sort of you see, you could even resolve the binary, but not at these low frequencies. So this is, of course, one option, which is astrophysical. And on the other hand, of course, there are many phenomena that can produce gravitational waves in the early universe. And of course, these sources are somehow, if you want, a bit more speculative. But on the other hand, the consequences of such a detection would be really profound. And so now I'm just mentioning some examples. For instance, one is phase transitions. As we know, they're very loud sources of gravitational waves. And for being relevant at these frequencies, the scale actually of the phase transition would be the QCD one. So of course there is, but okay, we know that in the standard model, this transition cannot, it's just a crossover. So it couldn't produce such an amount of gravitational waves, but of course with beyond the standard model physics, this is possible. And so this is showing this plot here. And another option is the primordial black holes, which has been investigated. But so what I don't know, how much time do I have still?
Almost 6 minutes.
6 minutes, okay, thank you. Yeah, so yeah, these are some possible sources, but what I'm gonna discuss here is cosmic strings, which is our own work. And so just some brief introduction to what cosmic strings are in the first place, just very short. They can arise as topological defects if there was a phase transition in the early universe with the right, let's say, topology of the vacuum, or they could also arise in fundamental string theory once the fundamental strings are stretched after inflation. And so this kind of objects, the cosmic strings, they can actually carry a very large energy density. So for instance, for grand unified strings or strings related to GATT breaking, you would have that the mass or the mass density, it would be like 1 Earth mass per kilometer. So these objects can indeed be very relevant cosmologically. And a way we can discuss the cosmic strings, in particular the ones that arise in field theory related to the phase transitions, is as a classical solutions of the equation of motions, in particular the vortex type of solution that was pointed out here in the 70s. And let me also mention very briefly that there are two types of strings, the global one and the gauge one. Gauge strings have a finite energy density, while global strings have a log divergent energy density due to the fact that there is a long-range interaction mediated by the Goldstone boson of the symmetry that is broken. But in a cosmological setup, this divergence is cut off anyway by the size of the horizon. So the strings are also, let's say, not pathological from this point of view when discussing cosmology. And let me also point that, okay, there has been some interest in studying these objects also in the context of Peccei-Quinn strings, which is also a case of global. But anyway, the ones that we are mostly interested in are the gauge ones, because here there is no massless decay mode besides gravitational waves. And so these are the ones that are expected to give a larger signal. Below the symmetry breaking scale, we expect these strings to be described effectively by the Nambu-Goto action, plus corrections, which are generically negligible in a cosmological setting, besides some possible exceptions. But in general, this is expected to be a good description for the strings. And so let me just briefly say that, okay, some defects are considered pathological or incompatible with the standard cosmology because they would come to dominate the energy density. This is a case, for instance, but for cosmic strings, this doesn't happen because there is a way in which the string network can lose energy, and this way is by chopping loops out of the long strings and then let these loops decay into gravitational waves. so that these defects are actually never dominating, but they rather track the evolution of the universe because their ratio between the energy density in the strings and the critical density is a constant, which is usually, yeah, so it is conveniently written in terms of G mu, where G is the Newton constant and mu is, as I said, the energy density of the string. So what is interesting, of course, for us is the gravitational wave spectrum, which is expected from cosmic strings. And the idea is basically that once you chop these loops, if they are smaller than the horizon, they're free to oscillate, and therefore they represent a long-lasting source of gravitational waves. And the total emission power is related to, okay, a gamma, which is just a factor, order 10 or so. It's basically related to their own energy density mu. And once the loops start oscillating, of course, they radiate energy, so they shrink, and their density instead redshifts with the expansion of the universe. The oscillation of the loop, of course, emits at frequencies which are related to the length of the loop and all the harmonics which come from that. And the power associated to the harmonics depends a bit on what is the small scale structure, let's say, of the loop. For instance, if the loop is dominated by kinks or cusps, this depends a bit on the shape, but okay. The basic spectral shape that we expect is shown in this plot for different values of the dimensionless constant G mu.
2 more minutes.
2 more minutes, okay, yes. And so as you can see here, there is certainly a possibility that cosmic strings can explain, or let's say have the right spectrum at the frequencies that are relevant for nanograph. And so let me just come to our results. So what we did was to indeed fit the contours or the preferred region provided by the nanograph collaboration with standard cosmic strings. And the idea is very simple. You have this sort of, sort of not exactly a power law spectrum for the string, but then you fit it at in the band at which nanograph is sensitive, and then you can basically extract from the parameters of the cosmic string. You can find what is the amplitude and the gamma. And now we can okay, we basically have two parameters. So one is the tension of the string, which is mu, and the other one is the size of the loops that are formed. And then, as you can see from these plots, it's certainly possible to explain the nanograph data with cosmic strings with the parameter space that is maybe better shown in this plot here, where we indeed vary G mu and the loop size. Let me also say that recent simulations are somehow pointing to values of alpha, this loop size of order 10 to the minus 1. So basically, this region here is somehow preferred in a sense with respect to the smaller values, but we provided, just very model independent, a very agnostic scan of all possibilities. And of course, it's a question whether, assuming that cosmic strings are responsible for the signal that is seen at nanograph, whether it's possible to see the signal also at the other experiments. And the answer is yes, because of the almost flat shape of the spectrum. But unfortunately, once you check this carefully, it seems impossible for at least the standard cosmic strings to give a signal that is observable at LIGO Virgo. And but of course it will be visible at other experiments such as LISA, and of course at the upgrades of the pulsar timing. And so this brings me to my conclusion. So there is certainly evidence for a common red process in the nanograph data, but the quadrupolar correlation is still inconclusive, although the monopolar and dipolar correlations are disfavored, which indicates that this doesn't seem to be one of the known issues that could spoil, let's say, the detection of gravitational waves. The several Pulsar collaborations are somehow joining their efforts. And for example, you can have a look at this talk by Jeffrey Osborne. And so we actually really expect some new results to be out in months, let's say. And of course, there are several astrophysical and cosmological interpretations of the signal in case it was confirmed to be due to gravitational waves. I hope I convinced that cosmic strings are, of course, interesting. And of course, such a detection would be certainly, I mean, would have very profound consequences for fundamental physics. And in this case, maybe nanograph just provided the first observation. Thank you.
Yeah, thank you so much. So let me have just one comment. I liked your article. I remember I read your article when you published it, because last year I had one stuff related to cosmic strings and FRBs, and we just used FRB data to constrain parameters of cosmic strings. So yeah, so this is just to relate theoretical stuff with the observation stuff, and I think this is a good way. Thank you.
Yeah, thanks.
So any other quick question or comment from the audience? I think no. So thank you so much, Simon. So would you please, if you stop sharing the screen, and let's welcome our next speaker. Yeah. So our next speaker is Xiao Rosa. I'm sorry if I'm pronouncing it in a incorrect way, but yeah. So you are going to talk about the thick brain structures in generalized hybrid metric palatino-gravity again, right? So in the beginning, we also had something about this palatino-gravity. So
that's true. We had Alberto, I think, who spoke about this theory as well in cosmic strings.
Yeah,
and,
yeah. Yeah, so you can start.
Thank you very much. So I am not going to speak about anything related to cosmic strings, but I think this is still the parallel session where this work is most adequate. So thank you very much for accepting my talk here. I'm going to talk about thick brain structures in hybrid metric-Platini gravity. This is a work done in collaboration with Douglas Ferreira, Dionísio Bazeia, and Francisco Lobo. It was published in here. So if you are interested, we can discuss, and I can also point you to more relevant articles. So the first thing I want to say is that since I'm talking about modified gravity, I think the first thing one must motivate is the study of modified gravity, given that general relativity is so successful. And the thing is that general relativity has many problems, like no quantum description of gravity, the need for dark matter and dark energy in cosmology, exotic matter in wormholes, and of course, the existence of singularities both in cosmology and in black hole solutions. So one thing people do to solve these problems is to recur to modified gravity, which can be done in many different ways. The first way is by adding extra fields to the action, like scalar fields, vector fields, and tensor fields. But this can also be achieved in another way by adding other higher order terms. And sometimes these two approaches are connected to each other, like, for example, between f of r and scalar tensor theories. So in this work, I will be dealing with the generalized hybrid metric-Platini gravity. This theory is described by an action of this form. We have a function of two Ricci scalars. The first Ricci scalar is the Ricci scalar of the metric G, and the second one is written in terms of an independent connection. So we have two independent variables in this action, the metric G and the connection gamma hat. We deduce two equations of motion. The first one is the field equations for the metric, and the second one is the equations that relate these two Ricci scalars with each other. As you can see, the theory is very similar to f of r, with the difference that we have one extra term here. So if we didn't have this term, this would be normal f of r. If we consider the hybrid metric-Platini version of f of r, we get this extra term here. So this is very similar to what is already known from f of r. This equation of motion for the connection, this relationship between r and curly r, it comes from this equation right here. This is exactly what comes from the variational method from the connection. This implies that there is a new metric conformally related to G, which is Levi-Civita to this connection. And so we get this, this equation here that relates the Ricci tensors of two conformally related metrics. Now, this equation is easier to deal with than this one, so this is usually what's taken into account. Now, the thing is, as I said before, sometimes one can make a parallelism between the geometrical representation and the scalar tensor representation. So in here, this is exactly what I'm going to do. I'm going to define two scalar fields as the derivatives of the function f with respect to r and curly r. And also, I will define a scalar potential of this form, depending on the function f and the scalar fields and also r and curly r. And in the end, we can write our metric, our action in this form. So this looks like a Brans-Dicke with two scalar fields, but one of the scalar fields as a kinetic term, the other doesn't. And we also have an interaction potential V. So in here we have three equations of motion, one for the metric G and one from each of the scalar fields. This is what we get. The important things to care about is that only the scalar field phi is coupled to matter. The scalar field psi is not coupled to matter, but it has a kinetic term, which is expected from the action. And also we have the field equations, the modified field equations from this action, which again are very similar to Brans-Dicke, with the exception that we have two scalar fields instead of one, and only one of the scalar fields has a kinetic term. Now, we are interested in studying brane world configurations. For the brane world to exist, we need some kind of source matter field to create this brane world. And we are going to describe this source field by a single scalar field with a kinetic term and a potential. So the stress energy tensor for this scalar field is given by this, again, with a kinetic term and a potential. And if you vary this equation with respect to the scalar field, you will find also the equation of motion for the scalar field, which is a simple Klein-Gordon equation with a given potential. Now, using a scalar field like this, you can produce a spacetime that is 5-dimensional. And this is the general form of the spacetime that we are going to take. So in here we have the Minkowski spacetime in 4 dimensions. So this mu and nu indices run from 0 to 3. This function here, a of y, where y is the extra 5th dimension, is called the warp function. And so in the end, if you insert this metric into the equation of motion for the scalar field, plus the two equations of motion for phi and psi and the field equations, you will get a total of 5 equations. 2 independent field equations, one for the extra dimension y, and another for all the other dimensions because this is isotropic in the 4-dimensional spacetime, plus 3 scalar fields. One is the source field and the 2 are the gravitational scalar fields, in a total of 5 equations. The number of unknowns we have is 6. We have the warp function, this function right here. We have the 2 gravitational scalar fields phi and psi that come from the action. We have the interaction potential between these 2 scalar fields. And then we have the source scalar field, this one, and the source potential field, which is this u right here. The thing is that if you take the derivative of the first field equation and use all the other equations to cancel terms, you'll verify that, in fact, one of the field equations is not independent. So you only have 4 independent equations in this system. Even though you start with 5 equations, one of them is dependent of the others. So in total, you have 4 different equations that are independent. If you have 4 equations that are independent and you have 6 unknowns, this means that you can choose 2 constraints to close the system and find your solution. In here, we are going to use constraints on the warp function and on one of the scalar fields. We choose the scalar field phi because the scalar field phi is not coupled to matter. And so to impose a constraint in the scalar field is easier than to impose a constraint on the scalar field psi, for example. And this is what we get. We choose these particular forms of A and phi for 2 reasons. Let me motivate these choices. The first motivation is that the warp function y must be asymptotically proportional to minus modulus of y. And we want this to be true because if you remember from the previous slide, we have the warp function in the exponent of this term. So if for plus and minus infinity, we have a approaching minus modulus of y, what happens is that this term goes asymptotically to 0. So this is asymptotically flat, pretty much. which is exactly what we want. The motivation to choose this form of phi is just if you are approaching a space-time asymptotically that is asymptotically flat, then in principle, your gravitational fields, your extra gravitational fields must be constant. So you choose this kind of thing to guarantee that when y goes to plus or minus infinity, this scalar field approaches a constant, but close to the brane, which is at y equals 0, there can be some different behavior of the scalar field phi, which in this case we choose to be an hyperbolic tangent. Now, using these two scalar fields, with the scalar field and the warp function, we can insert these into the equations and compute the solutions for the source field, the matter source field, and the matter potential. And what we see is that the source field is a kink. So for different values of the scalar field psi, we have different behaviors of the source field. And as you can see, it always looks like a kink. For very small values and or big negative values of psi 0, this is pretty much just a normal kink, which is consistent with the fact that the potential for this scalar field is just a potential barrier at the origin. Same thing if we decrease a little bit the value of psi 0, but something nice happens when we go to smaller absolute values of psi 0. If you look into the origin of this plot, this form of the source field is not a kink anymore. It's a double kink. It makes a kink all the way to the origin. It crosses the origin horizontally, and then it gets a second kink after the origin. And this is consistent with the form of the potential we defined, because in this case, the potential is not a single potential barrier at the origin. It is actually, I'm sorry, the plot should be zoomed in here. Unfortunately, it's not, but I hope you can see it, that this potential here is actually a double barrier. It increases, decreases again up to the origin, and then increases again. So this double potential barrier in the matter potential produces a source field that is a double kink instead of a single kink, which is a very nice, a very interesting result, let's say. Now, the thing is, these solutions, this thing that I've demonstrated here, it proves that solutions for brane world scenarios in 5 dimensions in this theory, they exist. But this is not enough to state the relevance, the physical relevance of our work, right? We have not only to show that these solutions exist, we have to show that these solutions are stable, because if they are not, well, it doesn't really matter. So let's make a stability analysis of this work. And by the way, I am choosing to present you this solution because this is the most interesting solution that we found. But if you look into our paper, if you are curious, and if you look into our paper, there are more solutions that we found and then we present in our paper. In a while, you're going to understand why I choose to present this one and why this one is the most interesting. So let's make a stability analysis. To make the stability analysis, what we have to do is to take our metric and induce a perturbation in the metric. In this case, the perturbation in the metric is described by this tensor h mu nu here. So we take our previous metric, which was just the Minkowski spacetime in 4 dimensions plus an extra dimension, and we induce a perturbation, a tensorial perturbation in the metric. What we have to do next is to propagate this perturbation. We induce this perturbation in the metric. This perturbation in the metric induces a perturbation in the Christoffel symbols, which in turn induce a perturbation in the Ricci scalar, which in the Riemann tensor, which induces a perturbation in the Ricci tensor, and so on and so forth. So in the end, we have to propagate this perturbation through all of the geometric variables and then insert the result into the field equations. If the field equations provide you something that is stable, then this means the solution is stable against the perturbation that we made. If the field equations show you that the equation is unstable, then this perturbation is unstable and the system cannot exist, at least in a cosmological lifetime, let's say. So when you do so, when you induce this perturbation in the metric and you compute everything to what happens in the field equations become something like this. So in the end, the scalar part, the trace of this perturbation, is described by somehow a wave function in 1 dimension, and where this z dimension is some redefinition of the y dimension. I made this redefinition just to make the equation look better, but this is basically something that depends on the y direction. And so we can write the equation, the field equation, as a wave equation for the perturbation in 1 dimension. Now the thing is, this equation is pretty much an eigenvalue equation for the perturbation. And we know that equations like this, they are stable only if the eigenvalues are positive. But lucky for us, the quantity that appears as an eigenvalue, this m squared, is positive because it appears squared. So this means that all the eigenvalues of this equation are positive. And so no matter what we do, no matter what kind of perturbation we do, the solution will be stable. So if the solution is stable, we can choose a value of m. Different values of m will be related to different modes of the graviton. And for example, we can take m equals 0, the simplest one, the 0 mode of the graviton, and see what happens. And what happens is the following. So if you choose different values of the scalar field phi, you will see that your stability potential, this uz, can have very different behaviors. If you choose, for example, a very small value for phi 0, you see that your stability potential is actually a potential well. And this induces a graviton 0 mode, which is a single peak at the origin. And remember that the brane is at the origin. But if you increase the value of this scalar field phi 0 to, let's say, 2, in this case, your potential well starts increasing at the origin, and eventually it becomes a potential barrier with a double potential well. And when this happens, sorry?
We have 3 more minutes.
Thank you very much.
Yeah.
When this happens, the graviton 0 modes splits into 2 peaks. This is what we call developing an internal structure in the graviton 0 mode. So what we prove here is that for certain choices of the parameters, this brane world develops an internal structure, which is something that we have already seen in other works, and this is pretty much consistent with the premise of the other works. In all the works where the brane developed internal structure so far, the thing is that it's the double scalar field system that induces the internal structure. This is seen, for example, in the block brane, where the double scalar field induces an internal structure. In here, it is a little different. The 2 scalar fields come directly from the theory because the theory has 2 degrees of freedom, a degree of freedom in the Ricci scalar and a degree of freedom in the Palatini-Ricci scalar. And we can use these 2 scalar fields to produce an internal structure in the brane world. Now, what's there to do? Well, these brane worlds that we have presented here, they are symmetric. So it would be very nice if we could use the same formalism to find asymmetric brane world configurations. And also, our approach in principle can be applied to other modified theories of gravity with 2 scalar degrees of freedom, like, for example, the f of RT gravity. We have also done this analysis in f of RT gravity. We have submitted this result. It's in here in the archives if you want to see it. It has been submitted. It's still under review. We are waiting for the referee's response. But basically, this proves that any theory, or at least the theories we have worked with so far, if they have 2 scalar degrees of freedom, they can produce brane world scenarios with an internal structure, a double peak internal structure. Thank you very much.
Thank you so much. Any questions or comments? Well, I have one question actually. So what is, okay, you say?
Yeah, you first. Okay.
Okay, so I have one question. What causes the appearance of 2 kings? I mean, what was the special about that potential that causes the production of 2 kings like that?
Well, this potential and this source field, they come directly from the equations. We think, we are not sure because the equations are highly nonlinear and they are a little complicated to interpret. But we believe that the same thing that's causing the double structure to appear is the same that's causing this this double kink in the source field. So there is a dependency on 2 scalar fields. One of the scalar fields may cause the kink, just the normal kink, to appear. The second scalar field might have like let's say an opposite reaction and may cause this extra structure to appear. What's important here is that even though the scalar field has a double kink, it still asymptotically tends to a constant and it's still 0 at the origin. So this extra structure doesn't change the overall behavior of the system, but it is somehow related to the development of a double internal structure. So we think that this has to do with the fact that the potential depends in two independent fields, and they might have, let's say, contrary behaviors affecting the source field.
Okay, thank you. Thank you.
Yeah, I have a question, Batu. Well, it's a very interesting presentation, but can you show me the line element delta ds square?
This one.
The one before.
Before?
Yeah,
Before is the equations of motion.
Oh yeah, no, that was okay. Yeah, no, the next. Yeah, you have here the bar factor. Huh?
Yes.
There must be a connection with the Randall-Sandra model. Okay.
Mm-hmm.
There you write in general the bar factor not only dependent on y but also your space coordinate, space-time coordinate x. So my question is, what will happen when you consider the contribution from the wild tensor, the projection on the brain? Did you consider that contribution also?
No, we didn't. We simplified it because the theory is a little complicated, and I'm still trying to. I'm new to this brain thing, so I'm still trying to learn. So we decided to start with the simplest case possible, where the warp function depends only in the extra coordinate. But that sure looks like something to extend the work to. Yes.
Yeah, you can do a lot of more in this model. And I have some question about the constant m square.
Yes.
Yes. Is there independent on the parameters of the model? Is just m squared just a constant from your differential equations?
This is dependent on the parameters of the model, but the point is that no matter what the parameters are, since this m appears squared, in the end the eigenvalue will always be positive, so it guarantees stability.
Yeah, okay, I understand.
Yeah.
Okay, thank you.
Thank you very much for your questions.
Okay.
Thank you so much. Thank you, Charles, right? Yeah. Thank you so much.
That's correct. That's correct.
Yeah, thank you. Thank you to all the speakers and participants. So it was a wonderful experience to have limited but quality talks. So it was a good day and good session. Yeah. So
and remember that you can send a contribution to the proceedings. Yeah. You know, and I appreciate it very much if you could send them. You have some time, maybe 1 year to prepare your contribution.
Yeah, 1 or 2 months. Yeah,
and you have 20 pages, so that is a lot.
Yeah. Okay. So is it fine if we all just have a virtual group photo?
For me, it's okay.
Because
very interesting. Yeah. Okay, so remember the contribution. You can send it to us or to the organization. It doesn't matter, but they will send it to us, Batul.
Yeah.
Do you remember? Yeah.
Yeah. I remember.
And we reserve 20 pages for you.
Yep. Yeah.
Okay, so, thank you very much for the contribution. And to the next time, and then in real time in Rome.
Yeah.
That will be much better. I prefer the real time conferences. You can meet people and you can talk, small talks with each other. I was in Rome. 3 years ago. It was very, very nice situation. Yeah, it's better. It is much interesting than virtual, for sure.
Yeah.
Sure. I met Roy Kerr and I had some small talk with him. It was very, very interesting. Yeah. Okay. See you, jongens. Bye bye.
So Reinhold, so is it fine if you just take a virtual group photo?
Okay. You know how to do that?
Yeah, we just all turn on our.
You are the expert.
Yeah. Let me check how to do this. I'm not
Maybe a
getting how screen of all the participants. Wait. Anyone can help me?
You can
maybe
just take
a
a print screen, a screenshot.
print
yeah.
screen. Yeah.
Yeah. We just need a screenshot.
So I can take it if you want. Do you know how to do it?
I'm not getting it. Actually, I just want to get a screen with all the participants. So I think maybe
You have you
we
should have
all-
a print screen button in your keyboard that takes it for you.
yeah. Maybe it works if we just all mute our mics. Maybe it happens. No, sorry.
Do you know if the parallel sessions are also recorded?
Yeah.
I guess so, eh?
Yeah. Every parallel session is being recorded.
Okay, did you make a photo?
I think not in a proper way, but I have tried to do it. Okay, I have tried it, but it's not a good thing.
Okay.
Yeah.
Well, bye-bye.
Bye.
Till next time.
Thank you very much.
Take that. Over 3 years in Rome.
Yeah,
Okay, bye.